In this video, we discuss the method of variation of parameters. And first, we're going to discuss when to use the method, and then we'll discuss the derivation of the formulas used in the method. Now, this is the one method in this course where I actually let you skip some steps. I let you skip some steps because there's a lot of algebra, just pages, it seems, of algebra that will come up every time you use this method. And I think if you see where it comes from once, I think going through all that algebra is not necessary, but I want you to see where it comes from at least once. So that's what this video is about. Now this method, variation of parameters, is allowing you to solve a non-homogeneous equation. So this does tend to be a little bit more complicated or less intuitive than the method of undetermined coefficients. So I recommend that you use the method of undetermined coefficients when you can. So we will use this method to find y sub p. When, let's say when either the corresponding homogeneous equation does not, have constant coefficients. So we're going to see how to solve homogeneous differential equations that do not have constant coefficients. In the next lesson, we're going to talk about Cauchy-Euler differential equations. So with Cauchy-Euler differential equations, the corresponding homogeneous function does not have constant coefficients. So you'd have to use variation of parameters to find y sub c, or y sub p, excuse me. So you're going to use this when that corresponding homogeneous equation does not have constant coefficients, or the right-hand side does not have the right form. The right-hand side is not an exponential function, a polynomial function, a sine or cosine function, or a finite sum or product of those. If just one of these is satisfied, then you have to use variation of parameters. Basically, I'm saying if method of undetermined coefficients does not apply, you have to use variation of parameters to find y sub p. In order to derive the method, we're going to focus on a second order differential equation now. So let's say you've got a second order equation that looks like this. We've got some function times the second derivative of y with respect to x, plus a function times the first derivative of y with respect to x, plus a function of x times y equals g of x. Oops, not f of x. I'm going to call that g of x over there. Now, in order to use this method, we need the coefficient of y double prime to be 1. So let's take this differential equation and divide out that a sub 2 of x. And I'm going to switch to prime notation now. So this will be equivalent to y double prime plus some function of x times y prime plus some function of x times y equals a function of x. Now, if this is our non-homogeneous second order differential equation and our goal is to find y sub p, well, we know a couple of things about y sub p. If y1 and y2 are solutions to this differential equation, or excuse me, if y1 and y2 are solutions to the corresponding homogeneous equation, that's what I should have said, that's what I meant to say. So that would be y double prime plus p of x times y prime plus q of x equals, or times y equals 0. If y1 and y2 are solutions to that, then we know that y sub c, that's the complementary function, is c1y1 plus c2y2. So we've got that much. Now, we also know that y sub p can't be a constant times y1, because if y sub p were a constant times y1, it would force the right-hand side to be 0 if we substituted it in, and we wouldn't get that f of x, which is supposed to be non-zero. And we're assuming f of x is non-zero because we're thinking of this as a non-homogeneous equation. So y sub p has to be linearly independent from y sub 1. And y sub p also has to be linearly independent from y sub 2. So remember when we did reduction of order, and we said if we have a solution y1 and we're looking for y2, since y2 has to be linearly independent from y1, y sub 2 has to be u times y sub 1, where u is a non-constant function. If you don't remember that, that's okay, just look back at the videos. But that's what we said. We said if y sub 2 is linearly independent from this guy, y sub 2 must be a non-constant function times y1. And we just have to find that non-constant function, and then we did using reduction of order. Similarly, y sub p has to be linearly independent from both of these. So this is what we're going to do. We're going to let y sub p equal u1 y1 plus u2 y2, so that it's linearly independent from both y1 and y2, where u1 and u2 are functions of x, and they're not equal to constants. So y sub p is equal to this for some unknown functions, u1 and u2. Now we're going to assume that we know how to solve the corresponding homogeneous equation, or at least we have two linearly independent solutions to the corresponding homogeneous equation, so we can find y sub c. So the question is, if we know y1 and y2, how can we find u1 and u2? Well, it turns out we're going to do exactly the same thing that we did with reduction of order. We're going to assume that this is the form of the solution, and then we're going to get a different differential equation that involves u1 and u2, and we're going to use that equation to solve for u1 and u2. Okay, now let me write down all of our assumptions before we do this. So we're assuming that y1 and y2 are known solutions to DEH, that corresponding homogeneous equation. We're assuming that y1 and y2 form a fundamental set of solutions to that second order homogeneous differential equation DEH. We're assuming that P of x and Q of x, and of course F of x, are known. The only unknown in this differential equation is y. These are known or given functions. And of course, we're assuming that f of x is not the 0 function. Or in other words, we're assuming that the DE is non-homogeneous. Okay. Given that all that's true, and we're assuming y sub p has this form, let's find an equation that u sub 1 and u sub 2 have to satisfy. Now, you're only going to have to go through this once, and it's just because I want you to know where the solution method comes from. So we're saying y sub p is equal to u1 y1 plus u2 y2, where u1 and u2 are non-constant functions. So let's take the derivative. This is a function of x times a function of x, so is this. So we're going to have to use the product rule for both of them. So we'll get, according to the product rule, derivative of the first times the second undifferentiated plus derivative of the second times the first. And then we add over here, derivative of the first times the second plus derivative of the second times the first. It's a second order equation, so we've got to take the derivative again. We're gonna have to use the product rule 4 times here. Just for this first piece, we're gonna get 2 terms. Derivative of the first times the second plus derivative of the second times the first. That's that piece. Then we're adding, again, next piece. Derivative of the first times the second plus derivative of the second times the first. Second piece. Third piece. I know it's tedious, guys. That's why you only have to do it once with me. But I want you to know where this method comes from. Derivative of the first times the second plus derivative of the second times the first. And if you're saying to yourself, oh, this is tedious, remember you're watching on YouTube, you can watch it at twice the speed if you want to. That's what I do when I'm trying to get through a video. I need the information, but I need to see it fast. It's totally fine with me. Just make sure that you got the information. Again, derivative of the first times the second plus derivative of the second times the first. Okay, now let's look for like terms. Do you see any like terms in there anywhere? Well, looks like I've got 2 of them. I've got u sub 1 prime times y sub 1 prime and another one of those, u sub 1 prime times y sub 1 prime. So I've got u sub 1 double prime y sub 1 plus 2 of those, 2 times u sub 1 prime y sub 1 prime plus y sub 1 double prime times u sub 1. And that took care of these 4 terms. Now I'm going to do the same thing, but with the u2 terms. Notice that I've got, so I think there's a mistake here somewhere. This was derivative of the second times the first, and that was supposed to be primed. There we go. Now that that's corrected, this term and this term are the same. So I've got 2 of those. It's a little bit hard to see because of the blue highlighter, but both of those are primed. So this is u sub 2 double prime times y sub 2, and then I've got 2 of these guys, so that's 2 times u sub 2 prime times y sub 2 prime, and then the last one is y sub 2 double prime times u sub 2. Okay. Now, the assumption is that this function y sub p satisfies this non-homogeneous differential equation. So we're going to substitute all of this into this non-homogeneous equation. And I'm going to do the same thing that we did when we were doing reduction of order. I'm going to add vertically because it'll make it a little bit easier to see any like terms. Okay, so we're substituting into this differential equation. We've got y double prime plus p of x times y prime plus q of x times y equals f of x. And we're assuming that y sub p is a solution of this equation. And we're saying if y sub p is a solution of this equation, what do u1 and u2 have to satisfy? And it would have to satisfy this. So let's actually do that. Got y sub p double prime here. I want p of x times y sub p here, y sub p prime there, and q of x times y sub p on this line. So I'm just writing everything over again. Y sub p double prime is this expression with 6 terms. It's got a lot going on. And then I have p of x times y sub p, which was, or y sub p prime, which is right here. Should be u2 prime, y2 plus y2 prime, u2, okay? And then we're adding q of x times y sub p, which was the u1 y1 plus u2 y2. And all of that has to equal f of x. We add those together. Okay. Now, I know this looks like a lot, and it is, but it can be simplified quite a bit because we know that y1 and y2 are solutions to the corresponding homogeneous equation. We know this is true. We know p, q, and f, and we've made that assumption that f is non-zero. Now, y sub 1 and y sub 2 are supposed to be known functions. So the only unknowns here now are u sub 1 double prime and u sub 1 prime and u sub 1. So I've got 3 unknowns like that. And then I've got u sub 2 double prime, u sub 2 prime, and u sub 2. So even though it looks like alphabet soup, and it kind of is, there are 3 unknowns for u sub 1, u sub 1, u sub 1 prime, and u sub 1 double prime, and 3 unknowns for u sub 2, u sub 2, u sub 2 prime, and u sub 2 double prime. So this is one equation with 6 unknowns. Ideally, we'd like to be down to one equation with 1 unknown or 2 equations with 2 unknowns because we know how to solve those. We don't know how to solve one equation with 6 unknowns. So we're gonna have to do some simplification. But because y sub 1 and y sub 2 are solutions to the corresponding homogeneous problem, turns out this simplifies a lot. So let's see how that works. In order to show that it simplifies a lot, I'm going to group all of the terms that involve u sub 1. So here's a u sub 1 term, and there's a u sub 1 term, that p of x times that, and q of x times that is a u sub 1 term. So this equation here is equivalent to this, and I'm going to factor out that u sub 1. I have u sub 1 times y double prime, y sub 1 double prime, plus p of x times y sub 1 prime, plus q of x times y sub 1. So that's the u1 terms, and then the u2 terms are similar. So I've got a u2 term here, and I've got a p of x times a u2 term there, and a q of x times a u2 term there. So I'll factor out the u sub 2, and then I have u sub 2 times y sub 2 double prime plus p of x times y sub 2 prime plus q of x times y sub 2. Okay? And then we've got this other stuff plus everything else plus this guy and this guy and then we've got p times this quantity and there's no q left because I already took those 2 terms out, and this is all equal to f of x. Now remember, y sub 1 and y sub 2 are solutions to the corresponding homogeneous equation. That was our assumption. It's right here. It's a little bit hard to see. It's in the middle of this page here. We assume that we know y sub 1 and y sub 2, and they satisfy the corresponding homogeneous equation. So if I evaluate this left-hand side at y sub 1, I should get 0. And if I evaluate the left-hand side at y sub 2, I should get 0 as well. So that means this is 0. All 3 of those terms are gone. And y sub 2, or that left-hand side evaluated at y sub 2 is also 0. So all 3 of those terms are gone. So now we're down to this, and that's great because that got rid of our u1 and u2. Now the only unknowns are u sub 1 double prime and u sub 2 double prime and u sub 1 prime and u sub 2 prime. So I've got one equation with 4 unknowns now. I'd still like to have one equation with 1 unknown, or 2 equations with 2 unknowns, because we could solve that. Let's see, how do we get from there to here? Or from here to there? Well, here is a fact. And you may have noticed when you were using the product rule that this happened. If I take the derivative with respect to x of u sub 1 prime times y sub 1, according to the product rule, I get the derivative of the first times the second plus the derivative of the second times the first. So I end up with a u sub 1 double prime times y sub 1, that's there, and then one of these guys, not 2 of these guys, but one of these guys. And it's going to be exactly the same if the subscript was a 2 instead of a 1. We'd have derivative of the first times the second plus derivative of the second times the first. And the first was u sub 2 prime. So this is equal to this. I only need one of those instead of 2 of those, though. So if I wanted, I'd have the derivative of u prime, or u sub 1 prime times y1 plus u sub 2 prime times y2 is equal to the sum of these two guys. Sum of these guys up here. Okay, so I can take this and I can write it differently. This is the derivative with respect to x of u sub 1 prime y sub 1 plus u sub 2 prime y sub 2. And then there's going to be an extra u1 prime y1 prime and an extra u2 prime y2 prime from right there, plus p of x. And do you see how this helped us? This fact helped us? Maybe not. Let me show you. That should be a 2. That fact helped us because it got rid of that that u sub 1 double prime and that u sub 2 double prime on this in this equation. Now, what are the unknowns here? U sub 1 prime and u sub 2 prime are unknown. I just talked about those, and I just talked about those. So the only unknowns in this equation are u sub 1 prime and u sub 2 prime. So now I've got one equation with 2 unknowns, and I would really like to have 2 equations with 2 unknowns. So this is what they do. I don't know actually who came up with this method, but whoever came up with this method said, let's let this expression here, which actually appears twice, here and here, let's let that be 0. Let's assume that that equals 0. If that equals 0, well then what has to be true? If this expression equals 0, then this function, or this sum of 2 functions, must be equal to f of x. And check it out, guys. That's 2 equations and 2 unknowns. I don't know if you're excited about this. I'm excited about this because you know how to solve 2 equations and 2 unknowns. You've been solving 2 equations with 2 unknowns since high school. If you ever solved a system of equations like this, you've done this before. Now, there are functions here instead of variables, and the coefficients are also functions, and they're not these constants, these integers. But we can solve this in the same way that we can solve this. You probably have never been exposed to this idea before, at least not at TCC. We don't have time to cover it in our pre-calculus class. But this system of equations can be solved with something called Cramer's rule. If you take linear algebra, I'm pretty sure your linear algebra teacher will show you Cramer's rule. And in order to use Cramer's rule, you have to write this in a different form. So let me show you how to do that. Basically, we want to write this system of equations as the form of a matrix times a vector set equal to another vector. And the way you do that is you take the coefficients that are right here. So 3 and 5, they go here in the top row, and -1 and 6, they go in the bottom row. These two numbers, they go in this column vector over here, and our variables x and y go here. Now, if you're not sure how this comes from this, it has to do with matrix multiplication. If I'm taking a 2 by 2 matrix like this, and I'm multiplying by a 2 by 1 matrix, since those agree, we can multiply them. The resulting matrix has dimension 2 by 1, so 2 rows, 1 column. These are rows by columns, rows by columns. Now, the way you actually multiply these guys together is like this. You're going to take dot products. So you're going to look at this top row and this column, and you're going to take a dot product. So this times this plus this times this is the first row, first column entry over here. So if you take the dot product of the first row with the first column, you get the first row, first column entry over here. So this is saying 3 times x plus 5 times y equals 10. And that's that first equation. Now, for the second line here, well, that corresponds to that second equation up there. You're going to take the second row in the first column. If you take the dot product of the second row in the first column, you get the second row, first column entry over here. That's a top row, first row, second row, first column, because there's only one column. So you take the dot product of this guy with this times this plus this times this equals this. So -x plus 6y equals -2. So that's that. Okay, now here's Cramer's rule. This is really cool. I don't know if you remember from pre-calculus, but if I'm solving the system of equations, I've got a line and another line, and I'm trying to figure out where the lines intersect. Cramer's rule tells me how to find that point where the lines intersect really easily. It says, provided that the determinant of this matrix is non-zero, so that this system of equations has a single solution, then the following is true. If you want to find x, all you have to do is take the determinant of this matrix. Well, let me do this in general first. So let's say you've got some system of equations, and you can write it like this: a, b, c, d times the vector xy equals ef over here. Now, according to Cramer's rule, the x value, that's the value of our first variable here, is given by this. You take the determinant of this matrix that goes in the denominator. As long as the determinant of this matrix is non-zero, you can do this. That means the system of equations has one solution. In the numerator, you're going to have a determinant of a different matrix. All you do to find this different matrix is you take this right-hand side, the EF. For the first variable, you swap out that first column with that EF from the right-hand side. You leave the second column alone. So you evaluate this determinant by multiplying across this diagonal, multiplying across that diagonal, and subtracting, and you do the same thing with this. That divided by that, that's your x value. And for y's, it's very similar. Since that's our second variable, rather than switching out that first column with the E and F, we're going to leave the first column alone, and we'll replace the second column with E and F. And if you evaluate that and divide, you get y. You do that here, you get x. And what's amazing is that actually gives you the point of intersection of those two lines. Isn't that awesome? I think it's awesome. Okay, so we can apply that over here. We just have functions instead of integers and variables x and y that represent numbers, but turns out Cramer's rule still works. This can be written in this form. Our unknowns are the functions u1 prime and u2 prime. The function on the right-hand side, functions on the right-hand side are 0 and f of x, and the functions that go in this matrix are the coefficients over here. In the top row, we've got a y1 and y2. In the bottom row, we've got y1 prime and y2 prime. Do you recognize that? I hope you do. I hope you say, if I take the determinant of that, that's the Wronskian of y1 and y2, and you would be absolutely right. Now remember, if y1 and y2 are linearly independent, that Wronskian is non-zero. So when you divide by that Wronskian, you're going to get something that's non-zero, and it's going to work out just fine. So this is the matrix version of this equation according to Cramer's rule. U1 prime is equal to this. You put that Wronskian in the denominator. I'm just going to call that W. And in the numerator, we're going to call it W1. You're going to take the Wronskian, you're going to switch out that first column with the 0 and f of x, and leave the second column alone. That's U1 prime. And to get U2 prime, you do the same thing. So U2 prime satisfies this. Except instead of swapping out that first column for 0 and f of x, you swap out that second column for 0 and f of x. Now, it can be hard to remember what it was we were doing, but remember we were trying to find y sub p. And y sub p is u1 y1 plus u2 y2. Well, it turned out that if y sub p was a solution to this non-homogeneous differential equation that we have right here, and y1 and y2 are solutions, then u1 and u2 prime, or u1 and u2 have to satisfy this equation, which simplified to this equation, which simplified to this equation, which simplified to these two equations and two unknowns. If these are satisfied, then this is satisfied. So we said, if y sub p is equal to this, then u1 prime and u2 prime have to satisfy this. Or alternatively, u1 prime must be equal to this, and I'll call this matrix W1, and this in the denominator, that's the Wronskian of the fundamental set of solutions. That's W. And u sub 2 prime is equal to that. Remember, you're trying to find u sub 1 and u sub 2 so that y sub p can be the form that we set at the beginning. So now you've got u sub 1 and u sub 2 prime, and I'll call this matrix W2. That means that u sub 1 is the antiderivative of W1 over W. Because you know it's derivative, you want the function, you want to get the function back, you take the antiderivative. And u sub 2 is the antiderivative of these two guys. Again, these are known functions. And once you have those, then you know what y sub p is. Y sub p is u1 y1 plus u2 y2. Isn't that nice? I think it's nice. Okay, so, and then of course the general solution is y equals y sub c plus y sub p. Now, I'm not going to have you go through that every time because as you can see, there's quite a bit of differentiation and then algebra, and then you'll say, oh, y sub 1 satisfies the equation, and so a bunch of terms cancel and a bunch of terms cancel, and you'll end up here, and then you'll have to say, oh, well, I can write this as the derivative of this product, and every time that will happen. So we're going to skip a bunch of steps, and this is how we're going to use variation of parameters instead, because we've gone through the derivation once. The first thing that you're going to do when you follow this method is this. First, you're going to find y1 and y2, or alternatively, you're going to solve the corresponding homogeneous equation. So you're finding that y sub c. And then once you find those, you're going to let y sub p equal u1 y1 plus u2 y2, where u1 and u2 are non-constant functions. And then we're going to say, we're going to skip a bunch of steps. The one method where I will let you, and you can still get full credit on your problems in this class, we'll say if that's true, then by variation of parameters, the following is true. u1 prime is equal to w1 over w, and u2 prime is equal to w2 over w, where w is the Wronskian of y1 and y2. w1 is the Wronskian almost, but you switch out that first column with 0 and f of x. And w2 is almost the Wronskian. You just leave the first column alone and you switch out the second column with 0 and f of x. So you're going to evaluate these. That's going to give you u1 prime and u2 prime. You're going to choose the constants of integration to be 0. And that'll make more sense when we talk about it, when we're solving an actual problem. It has to do with having a constant times y1 as part of your y sub p and a constant times y2 as part of your y sub p. You don't need it. So we're going to let those constants be 0. And then once you do that, you have u1 prime, or well, you had u1 prime and u2 prime. I guess I got ahead of myself. Then after you have u1 prime and u2 prime, you're going to anti-differentiate to find u1 and u2. That's when you let the constants of integration be 0. Sorry about that, I almost skipped that step. So now you've got u1 and u2 without any constants of integration. Then once you've got your u1 and u2, then y sub p is just u1 y1 plus u2 y2. And then the general solution is y equals y sub c plus y sub p. And y sub c is a constant times y1 plus a constant times y2, and y sub p is equal to this. So that's the method. And we're going to do an example in another video, but I want to show you how you would handle this if the differential equation was a third order differential equation. So let's say we've got a non-homogeneous third order linear differential equation. So you've got y triple prime plus a function of x times y double prime plus a function of x times y prime plus a function of x times y equals f of x. Now again, f of x is the function you have on the right-hand side when that coefficient of the nth derivative of y with respect to x is 1. This must be a 1 for us to correctly identify f of x. If you don't divide out the right function, your function f is going to be the wrong function and the formulas that we give you won't work. So make sure you have a 1 in front of your y double prime, or if you're looking at a third degree or third order differential equation, make sure you have a 1 in front of the y triple prime. So if you have a third order DE and y sub 1, y sub 2, and y sub 3 are 3 linearly independent solutions of the corresponding homogeneous problem. So it's going to look exactly like this, but with a 0 over here. Then u sub 1 prime is equal to w1 over w, where w is still the Wronskian of those 3 functions. And I bet you can guess what we'll have in the numerator here. It's going to be just like the Wronskian. But in that first column, you're going to have a 0, 0, and f of x. For u sub 2 prime, we'll call that w sub 2 over w, and w stays the same. And the first row or the first column and the second column stay the same, but your middle column is going to be replaced with 0, 0, and f of x for w sub 2. Maybe this is misleading. There's actually like 3 terms here and 3 terms here. I don't like the way that looks. Let me be more explicit. So we'll have y sub 1, y sub 1 prime, y sub 1 double prime, y sub 3, y sub 3 prime, and y sub 3 double prime. And you swap out the second column with 0, 0, and f of x when you're solving for u sub 2 prime. you still have the Wronskian in the denominator. And u sub 3 prime is equal to W3 over W, where W3 looks just like the Wronskian. You just swap out that third column with 0, 0, and f of x. Now, I will have you do one like this in the homework. I think maybe 2 like this in the homework, but no more than 2. But there's no way that I would do this or ask you to do something like this on an exam, just because computing a bunch of 3x3 Wronskians with functions, or 3x3 determinants, excuse me, with functions rather than integers is quite involved. It takes a long time. But I do want you to be familiar with how we find y sub p. In this case, y sub p, so u1 prime, u2 prime, and u3 prime look like this. And y sub p has this form, u1y1 plus u2y2 plus u3y3, because y sub p has to be linearly independent from y1, y2, and y3. Okay, I know that was a lot, but this is the method we're going to follow when we do an example. I'll see you in the next video to do an example of variation of parameters.